thank you all for coming. We're the last breakout before we get to relax a little bit and have a drink and socialize again. So, the full room is awesome. I appreciate everybody coming to listen to us talk about heavy wall pipe trends and best practices. I'm Jesse Smith. I'm currently our technical support supervisor. I've also spent a lot of time in our training department with Macro University. So I've been involved with training and field support for going on 10 years. I have with me Matt Hennigan, and I'll let you introduce yourself.
Hi guys, welcome, thanks for coming. My name is Matt Hennigan. I'm a training specialist here at McElroy. I've been here for about 10 years, 13 years. It gets confusing because I was an electrician with the contractor before, so it blurs together. I've been here for a while. I've been
around
for a while. Yeah, but training specialist now.
With McElroy or at?
Yeah, it's training specialist now. I do some operations training, but we've been kind of going down a path of doing some technical training with the I-Series, so good stuff there. So hopefully this will be good stuff. If I flub too much, I'll buy you a beer after this.
Perfect. And we have a third name on the list of presenters here, and man needs no introduction, but in the back we have Jim Johnston, who is one of our resident experts on the subject. And as I look around the room, I see a lot of folks in here who are probably experts on this subject and others. So I think as a group, I think we're going to have a really good conversation around the topic here. So I'll give you the roadmap for what we're going to talk about. So we want to talk about what is heavy wall fusion. Try to put a definition to it. And there's some work happening around this that we'll talk about that's going to help us with that. We want to talk about the increased usage that we've been seeing. We'll talk about why. That's the trends that we're seeing. We pulled some vault data together, and we can help you see where heavy wall fusion is and where it's going and what we think is causing it. And then we'll talk about what we're going to call caution flags, and sticking with our race theme here. Things that we need to be doing with our customers and with folks that we're selling heavy wall pipe to that are bidding these jobs to help prepare them to be successful. So we're going to show you some things that you need to be paying attention to. And Matt's going to talk about what we'll call some best practices, some things that you can do to try to avoid some of the troubles that we've seen people run into. So hopefully these will be helpful to you. And lastly, we'll talk about some inspection and testing techniques that we're seeing folks use that they're having success with. So before we get too deep here, the green light has started, but I want to mention that there is an ASTM standard that is in the works specific to heavy wall fusion. It is not released yet, so it's going through the process of being balloted. So the things that we talk about today may not match exactly with what you see when that standard comes out, but we're talking about heavy wall fusion as we know it right now. So with that, we'll get started. So what is it, heavy wall fusion? Let's define it. For our purposes, we're going to talk about pipes with a wall thickness of, let's call it 2 1/4 inches or greater. You all are very well aware of how we can get to 2 1/4 inches. That could mean heavy DRs or not so heavy DRs, depending on what pipe OD is, and I'll give some explanations of that. But first, let's look at some vault data just to show you some of the trend that we're seeing. So the graph that you have up on the screen is joints with a wall thickness greater than 2 1/2 inches going back to 2018. So you can see the number at 2022 was pushing 60,000 joints in that year, and we're expecting an increase to push past 60,000 in 2023. So there is a continual growth in heavy wall fusion, and that's why we're here talking about this today. So why? Slide, please. We're seeing applications where we're requiring higher pressure. We all know that, right? That's why we need heavier walls. But just to give you an example of where that might be, we're seeing a lot of oil field applications where we're seeing DR7s and DR9s. Anything that we want the same benefits we get with HDPE systems and other systems in higher pressure applications that let us be competitive with other products. you're going to see heavier wall pipes. So give you an example of what that might be. 20-inch, very common size we see in the oil patch. DR11 gets you to almost 2 inches. You get to a DR9 and you're right there in heavy wall territory. You get to a DR7, which we see a lot of, and you are now in heavy wall fusion. That's when I think when we talk about heavy wall pipe, people immediately gravitate towards that's a DR7 or that's a DR9. That's what heavy wall means. Well, not exactly, because we're also seeing an increase in large diameter pipe. There was another breakout on this topic done, I believe, yesterday. But I think that when you look at large diameter pipe, you hear, well, what about a 54-inch OD? We get to a DR26, and we're already at 2-inch wall thickness. And DR21, we're already into heavy wall territory. I think that with the increase in large diameter pipes, you're seeing an increase in heavy wall pipes, and people that are fusing heavy wall pipe and don't even realize it because don't even realize that they need to treat it differently because they're hearing DR21 and DR26 as really common DR values with 54-inch plus pipe. So keep that in mind. You get to a DR17, you're 3 inches, and you're very well into heavy wall pipe. So just to reinforce that idea, I'll show you another graph. This is heavy wall joints by machine class. Again, going back to 2018, the blue bars on the graph being fusions done in the medium diameter range, which we're calling that through, let's call it T500. So the orange bars being large, which we're going to call that your 630 through your on up to your T1200 and larger. And it's pretty obvious that there's a significant difference in the growth in large diameter pipes, accounting for the heavy walls. So this is vault data that we pulled again going back through 2018 to 2022. So continued growth, what does that mean for the folks in this room? What do you need to do about it? If you're not doing some of these things already, I'll give you some examples of things that you can do with your customers to kind of prime them for success. And the way I'll talk about this is you need to know your customer. You all know the types of folks that you deal with. I kind of break into a couple categories when specific to this topic. Is you're going to have people fusing heavy wall pipe that don't know they're fusing heavy wall pipe, and I'll call these they don't have any HDP experience at all. And when you don't have experience, where do you go to get it? You go to get trained. You go out and you teach them how to fuse pipe. So you need to be having conversations about what they need to do differently with heavy wall pipe early on, so that they're prepped and ready. And then you have the old hand. This guy has done it all, seen it all, and he doesn't have any heavy wall fusion experience. Maybe he's been in natural gas, maybe irrigation systems, things like that, and bids a job that's going to be a heavy wall project, and thinks I've got the tools, I've got the know-how, I'm going to handle this like I've always handled it, I've always been successful. He's likely to run into some of these caution flags that we're going to talk about later down the line. So think about how you need to talk to that individual versus somebody who's brand new, who has no experience at all. It's going to be a little bit different. And then lastly, you want to find out who the decision maker is. That is really the person that you need to get to when we're talking about making changes to our procedures, to our equipment, to the way that we do business on these projects, so that they can implement these best practices and really set themselves up for success. So I'm going to shift gears just a little bit and start talking about the caution flag and how we get there. Okay, and there's a thing that we're really trying to point out here is when you do heavy wall fusions, there are things that are going to look different, feel different, and act different. And one of the things we want to talk about is our fusion beads. So I'll put this picture up on the board, and everybody's. So I don't know who's booing in the back, but we're familiar with this, right? This is TR33. Kind of gives you what a fusion bead's supposed to look like. Everything's supposed to be uniform, and everything's supposed to come out, to the right dimensions. And the reality is especially as materials change and things get different, this is getting harder and harder to come across. So how do we address that specific to heavy wall pipe? I want to point you toward technical note 51, which is polyethylene pipe butt fusion structure, process, and terminology. It's another PPI document. And this is the only place that I and others are aware of where you get a good depiction of what a heavy wall fusion bead could and often does look like. And it gives us, it points out the existence of two separate beads, one being a heat soak bead and the other being this melt puddle flow zone, which, for simplicity, I'm going to call it a heat soak bead and a fusion bead, because you really tend to get this double bead appearance because of the way this pipe acts during the heating process. So let me give you an example of how we get there.
So before you jump into that, Jesse, I think part of that typical training that we all have, back to that inexperienced person, is that with a traditional look at the bead, that double rollback bead is a negative. Everybody knows that means you did something wrong. And what he's about to show you is why that happens and why you need to educate people relative to heavy wall, because it does have a different morphology. It does have a different method that occurs. And so that bead's going to look different. And some people still have a TR33 gauge in their truck somewhere. And so this is one of those caution flags of know why it does it, educate your user.
Yeah, appreciate the clarification. So my crude animation on the board here, I've got two pipe ends and a heater in the middle. So we're going to bring our pipe ends up against our heater, and we're going to go through our process of starting our heat soak. We're heating at 4.5 minutes per inch of wall thickness. So by our definition of 2 1/4 inch thick walls, we're going to be north of 10 minutes heat soak on all these pipes. So a significant amount of time where that bead is developing, and as it develops, we're looking for beads in the 9/16, big heavy beads, and they grow when they further away from the heater. So they have the opportunity to start to cool and skim over as they grow further away from the heater, which causes them to act a little bit different than what we might train to, or what the TR33 picture would lead us to believe. So as that fusion is made, because of that skimming over that happens, the flow zone kind of comes up through the middle and pushes that kind of pre-cooled bead out in a different manner, which tends to get this double bead appearance. So a couple different ways that that resulting bead can look. You kind of have what we affectionately call the Mickey Mouse ears around here, where you have the bead that has the fusion bead has come up through the middle and kind of forced that melt bead up and out, and it never really looks like it rolls back and touches the pipe, which would not match what we would see in the chart in TR33. Or we have a bead that does kind of appear to roll over, but it almost looks like it rolled over and then shot out down the sides of the pipe, where we get a double bead appearance. And if you look closely, the initial heat bead is actually kind of holding the fusion bead up a little bit off the pipe. So to give you a real example of what that might look like, this is a fusion from a project that some of the folks in the room were involved in, but large diameter pipe, 63 inch, I think DR11 on that job, so heavy pipe, and you see the existence of this initial heat soak bead that is holding the bead that flowed up through the middle, our fusion bead, up and away from the pipe. So pretty common way for this to look. Here are some other examples of fusions that have been done with similar appearances. So they all vary just a little bit. You can see some slight misalignment might make it change a little bit. So I think the point is that you can't use the cookie cutter approach to what fusion beads are supposed to look like anymore when you're dealing with this heavy wall pipe. Now, all three of these examples are strips that were cut out to do bend backs on. They all passed. They were all data logged. Procedures were followed correctly. All that was documented, and everything was just fine with them. So just to kind of reinforce that, just because it doesn't look exactly like someone might think it's supposed to, doesn't necessarily indicate that there's a problem. So folks need to be prepared for that. I'll give you another example here of something that can happen. You see a left bead that has this double appearance that we're talking about, and a right bead that does not. And I know a lot of you in the room have probably seen similar situations where you have bead growth on one side that's different than the other. And we always talk about what bead uniformity means, and that's true in this case too. Bead uniformity is, a right bead is uniform to itself circumferentially, and a left bead is uniform to itself circumferentially, but they don't necessarily need to match. So different variables that can cause this with cooling from wind or whatever, but this is something that can happen to you as well. Okay, let's look at V groove depth, because this is another place we run into questions on, and I've got an image from ASTM F2620 up there. Everybody's probably familiar with this little excerpt that talks about V groove depth should not be deeper than half the height of the bead. And you can see in the image that V groove actually goes down past the surface of the pipe, and I think that's really the essence of what we're trying to get at with this particular potential problem. So I'm going to change the screen here and show you how we might apply this to a heavy wall fusion bead that has had this double rollback appearance. Same example we were looking at before. If you were to take that and look at the bead height, from the top of the bead to the pipe, that's the height, right? Okay, and then if you look at the V groove, without going in and measuring that, you could argue that that's probably just about half, or maybe a little more than half of the height of that bead. But that really doesn't tell the whole story in this case, because you have those heat soak beads that are actually holding the fusion bead up off the pipe. So we need to think about this thickness as being our fusion bead thickness. So if I was to take that thickness and roll it out across to the surface of the pipe as you would normally expect it to do, what you would really wind up with is a V groove depth of something like that. So you can't really think of it in the same way. You need to be prepared to answer that question during inspection. So really want to point that out as a thing that you really got to be prepared for, because if there's one thing that you're going to encounter from a quality standpoint, that's probably going to be it. So there are some other things that can be done to help mitigate some of these problems. So we're going to talk about how to avoid some of the caution flags that will come up, and I'm going to turn it over to Matt to talk about some best practices and lessons learned from some of the projects we've been involved with. So,
Awesome.
Thanks, everybody.
Was that you to work this morning?
I was running late, Thanks, sir. Appreciate that.
Matt, just real quick,
Sure.
one thing, Chip talked about F1 and you got a NASCAR picture up there. And
Yeah.
I don't really understand the rules of either one of those.
Hold on.
I do follow drag racing, and it's pretty straightforward.
All right. We'll see you guys tomorrow. I really hope that got captured on video. All right, thanks Jesse for setting the roadmap for that. I do want to talk about avoiding some cautions, so some best practices that we can take to be a little bit more successful. I'll just throw some of these up here. Pipe handling, alignment's a big one. Use of the data logger, we'll talk more about that. Temperatures, pressure ratings, and finally some testing and inspection. Before we get started, I was actually on the bus yesterday with Mike. We started talking about this a little bit. Some of this stuff you're going to look at and go, well, yeah, duh, that makes sense. Other things you're going to look at and be like, oh, maybe I didn't think about that. So we have a lot of folks that come through class that say, well, we've got a trailer with a job box with all our tools on it. It's ready to go. We just hook up. If we have a 2-inch to 20-inch job, that's what we take. And we've found in some of those cases that they might not have everything they need, or things might not be rated for the weights of this heavy wall pipe. So we'll talk a little bit more about that. So first thing out of the gate, we want to talk about pipe handling. We see guys that have equipment, whether it's a skid steer a mini excavator, stuff like that. They don't think about the fact that when they get to the job site, that skid steer might not be able to lift this stuff. So even unloading it to get prepped for the job might get them right out of the gate. So start thinking about the equipment that you need to use to maneuver this stuff around the job site. Part of that also is space. You might need more right-of-way, right? So you might have your job set up and you've had permits pulled for a certain amount of right-of-way. You might not have enough room if you've got to upsize your equipment. So just little things like that that you need to be thinking about before you can even get going on the job. So, of course, safety is always paramount, no matter what size or how thick the wall of the pipe is. This is a pretty good picture of things that we see quite a bit, where we've got 3 guys over here and a guy standing in between the 2 pipes. I've seen quite a few times where the straps that they're using aren't rated for the weight that they're going to be moving. We saw a bunch of it in Alaska. It's kind of scary when those straps break, right? You guys have probably seen that. So even just thinking about little things like, are my straps rated for what I'm going to be moving, right? So pipe support, always important. We've got an example here. 50-foot stick of 36-inch DR9 weighs about 80 to 100 pounds. So when you start thinking about supporting this heavier wall pipe, there's some things that you can do to get around that. So one of them is just adding more pipe stands, right? Seems pretty simple, but some people don't think about that. Also making sure, like I said, that the pipe stands that you're using are rated for the pipe weight that you're going to be handling. So that's also going to help you be more successful when you're aligning that pipe in the machine. It's going to take less stress off the machine and the operator. So it's got extra benefits there. Talk about pipe hole alignment. This is another thing that Mike and I talked about yesterday. When we put this pipe in the machine, what are we usually looking for? We're looking for that alignment of the outside diameter of the pipe. Well, the way that this heavy wall pipe is extruded, you've got to be paying attention to the inner wall as well, so the inside diameter as well. So this pipe, when it's extruded just by gravity as it's being pushed out, that gravity is having an effect on that material, right? So you can get something that looks like this. I've got a little crude little graphic here as well. So you'll see 2 pipe ends coming together. On the left, you got a thinner wall up top. On the right, thicker wall, vice versa on the bottom. This is what we're trying to get around. So one of the ways, this is an actual real life picture of that. This came from that same job in Alaska, and you can see right down here on the bottom, there's a pretty good mismatch of those pipe walls, so inside diameter. So you can see that outside diameter lined up pretty well. It's the inside that was the issue. So there's some ways to get around that. One of the easiest ways to do that is to just line the print line up. So once again, Mike and I were talking about this last night. I always think about it like, do you remember the Play-Doh Fun Factory thing where you put the Play-Doh and you pushes it out? I think about like when we're fusing this back together, I want to put it back together kind of in the same way that it was extruded, right? That's going to give us the best chance of getting that lined up. Makes pretty good sense.
So quick question here.
Sure.
Again, best practice, this gets those pieces aligned. We hear some sort of conflicting pieces out in the world. There are some people that align directly to the print line every time. We also have heard that there are people that do not allow you to align to the print line because they may be removing the OD bead and they want to be able to find that misalignment. Does anybody in here run into the ban on aligning print lines? Anybody had any issues with that? If you run into it, you don't have to be 100% aligned. You can have a little bit of rotation, say it's 10 degrees. You just want to be in that so that you're aligning as much of the walls as possible. Again, the only time that I've ever seen it was where somebody was removing the OD bead and they want to have a visual, they wanted to have a visual break on the print line to see where every joint was. But if you ever run into that, the idea is still to align as close as possible to that alignment. Obviously, if you get it together, you're back to the way it was extruded and came out of the Play-Doh Fun Factory.
I mean, the other obvious thing is, from a quality assurance standpoint, God forbid there is an issue in the pipeline, you want to go dig it up, you hope that print line faces north, right? So there's another reason for aligning it other than just with extrude. On top.
Awesome. We'll talk about data log. We talk about data loggers quite a bit. That picture that Jesse showed earlier with the double bead on one side, single bead on the other, we can take pictures with these data loggers. And we also have, you know, a graph that we can go back and validate that the procedure that we were using was correct. So there's a lot that we can do with the data logger. When we get into the heavier wall pipe, I utilize those two features quite often just because if there's any question, we can go back, check those photos, check that graph, make sure we were doing everything that we were supposed to be doing, right? So one of the other processes, speaking of data logging, everyone's favorite measuring drag. And we teach someone how to do this. How many of us have seen this once or twice, a couple times? Alan
I
didn't
know
dare
there's
right
more than
there.
that because I've taught it.
Right. Right. How about this guy? Where you hit the measure drag button, right? So Jesse was talking about earlier, sometimes you've got the old hand that's been doing the same thing the same way for 100 years and now he's teaching the new guy. Sometimes there can be some misconceptions that lead to some inconsistencies, right? So I'm gonna mix it up here a little bit. See if you can figure this out. Got three guys up here on the screen. Everybody recognize these guys? Got Nolan Ryan, pretty good pitcher. Think he's gonna work out. King Griffey Jr., these guys are all in different phases of their career, right? And then finally Steph Curry, probably the best three-point shooter ever to play the game. What are these guys?
Got some basketball fans.
What do these guys all have in common? Any guesses?
Make a lot of money.
They make a lot of money,
Been doing it a long time.
doing it a long time. That's a good one.
They work hard at what they do.
They work hard at what they do. They also all wear the number 30. Ring a bell? How many times have we heard, oh, just set that pressure, sir. Right? Yeah,
See him on the dialogue.
all the time, all the time. 30 is fine.
Yeah, how many rental machines have that written on the top, Joe?
Right. Right. So those kind of things, you know, do we think 30 PSI is gonna do anything here? No, this is heavy pipe, high drag situations. We have contractors that have special crews that just go in and do tie-ins, same situation. High drag scenarios, right? So those misconceptions can kind of lead to some inconsistencies, right? So we want to be paying attention to that. All three of those guys were pretty successful, right? You think they got that way by not practicing? No, like you said, and putting in the work, right? So that's what we have to do here. So anyways, wanted to throw a little curveball, fastball in there. So talking about measuring drag, have you guys all seen this on the I-Series? The manual drag setting? We put that there intentionally because there were some scenarios where that automated drag setting wasn't working. So we gave you guys the ability to go in and actually measure that drag so we get we're as successful as we can be, right? So talking about graphs, has anyone ever seen something like this? Little thermal expansion. Sorry, am I standing right in the way?
No, you're talking about where it
Yeah,
starts
see-
to go up
yeah.
right after you
Yeah,
do your
right.
shift sequence.
Right, so you
Yeah.
drop that. So those cylinders are full of fluid, right? And as that stuff starts to heat up, what's it doing?
It's expanding.
It's expanding and it's pushing out against that, which causes this to kind of rise. So is that an issue? No? What could you do as a best practice? I'll get out of the way so you can take a picture. Here, I'll even do this. So that's what we're looking at right there, right? So not that big of an issue. There's a best practice that you can do. Fernando, you got it? You want me to get in it? So best practice, we can just extend the heat soak. Once that drops down below where we need it to be, start your heat soak then. We can leave the control valve closed if we need to. We can also move over to level 1 or 2 in the I-Series, right? So that gives us the capability to control that. So talk a little bit about temperatures here. Alan, what temperature are we looking for?
400, 450.
All right. So we usually shoot right down the middle, right? 425, 215 in case of ISO. Best practice for heavy wall, there we go. We're gonna wanna go up to that higher end of that temp range, right? And so Mike, you and I were talking about that yesterday, and he asked, well, why do you do that? We think about having a pipe wall that's, you know, I saw some yesterday that are 4 or 5 inch thick walls. That's a lot of mass. And you put your heater up against that, guess what's gonna happen? It's gonna suck the heat right out of that thing, right? So if you're running at that higher temp range, you don't have to worry about it dropping below. So if you were lower than where we needed it to be, you could potentially drop out to the temp range to be undervalued, right?
You know, the other aspect is that after you've heated it, you've got your melt and everything's right, you're ready to open and close, is that a larger diameter heater plate takes longer to get up and get out.
Mhm.
And if you're starting off at 415, by the time you get it out, it could be 380.
Yep.
I'm just making this up.
Yeah, yeah,
But if you're at 450 and it drops 20 degrees, now you're at 425, whereas you want to be.
right.
So part of the heat is making it robust so that you maintain your heat.
Right. Good point. Thanks for throwing that in there. All right, so the other side of that, we're going to talk about pressures. So same thing, 60 to 90, we usually shoot right down the middle, 75 PSI for ASTM. So a little bit different on heavy wall. We're going to go to the lower end of that range, right? Jim, you do a pretty good job of explaining that because I've had some questions about that, and they're like, well, why don't we just use low pressure all the time? So do you mind expanding on that, please?
So the advantage of the high force fusion is it's still pushing out a larger mass and helping cool the process. But Harvey can talk about the rheology after the meeting quite a bit, but there is some processes that go on relative to the, basically, for lack of a better term, let's call it at the molecular level, at the material level, that this lets you control the speed of that expansion, control that joint just a little bit better. Again, the standard that's out there, 60 to 90 PSI, we know that lower pressure with the experience that's out there, that best practice shows that those lower pressures tend to work a little bit better with this material on those pieces. Give not a more robust joint, but just help with the process a little bit better. So from a best practice standpoint, heavy wall fusion run at that lowest end of that pressure. The new standards that Jesse referred to would lower that pressure more. Again, that's not out there today, so best practice is to run at the baseline of the pressure that we have out there today.
See, way better said than what I've done. Thank you.
Wouldn't you run into quite a few issues with hydraulic chatter?
Say that again?
Wouldn't you run into issues with hydraulic chatter?
Hydraulic chatter. Not that I've seen.
Or you're gonna be outside your specification.
Sure.
If you get too much chatter, it's gonna drop below that 60 interfacial pressure.
Are you talking on the cooling side where it starts to flutter?
And we've seen that when we've had to drop our pressure because we're using a fitting or fusing a fitting on one side and it's slipping because it's so high.
Right.
The pressure's so high, so we drop it down to 60 and then it drops below. So we have to cut it back out.
And Mike, if you've got a significant amount of what you're calling chatter for the rest of the room, if you're looking at a data logger graph, he's talking about up, down, up, down, up, down, up, down through the cool cycle. There's some other things that could be going on there as well, that might need to get addressed. So, it's kind of, in that scenario, it's kind of a process of elimination. Like how low can I go before I start having issues with dropping out of my specified range?
Right. I've seen that indicate a bad valve before, like that's, so.
And then, again, up here, what he's got is 65 plus or minus the 5. If you run right on 60, then, you're down to the measurement category of the piece. So typically I see people doing 65, and then that gives you a little bit of variance on how it gets dialed in and how it's measured, and if there's any chatter that you're not bouncing out of that 60 range.
Awesome. Thank you for the question. So I want to talk a little bit about some best practices for testing and inspection. So traditional bin back test, we're looking at a 1-inch wall thickness. So right out of the gate, that doesn't apply to us, right? Because we're talking about 2 1/4 and higher. So there's some ways that people get creative in testing these things. Have you seen some of this? Yeah, yeah. I mean, it's creative, right? Probably not the safest thing in the world. Yeah, so, yeah, just say no to this guy, right? So probably think of something better to do than this. So maybe you got a friend, you can call them up. They've got a better idea. Effective, yeah. Also, probably not the safest thing in the world. Watched a lot of MacGyver as a kid. Also, probably not safe, right? So let's think about some way we could do this that might be a little safer, a little more effective. Let's talk about the guided side bin tester, right? So this is good from 1-inch to 7-inch. It's incorporated the most current version of the F2620. It also happens to be backed by F3183. So the good thing about this, the real reason I like this test is you can actually do it on the job site, right? You can cut those samples out, plane them, do it right there. You don't have to send it off and wait for those to come back. It's on the fly, and we can measure all that there. So let's talk about some takeaways. Obviously using a data logger for all of the resources that it adds. I specifically like those pictures because they're worth 1,000 words, right? Use the higher end of those temp ranges, lower end of the pressure range, and then finally testing and inspection. I like the bin back test. So a little bit of review I want to go through. Jesse talked about educating ourselves, knowing our customers, knowing what they're doing, what applications they're using this for. Communicate early and often. Pretty self-explanatory. The tech reference, you know, he and I talked a little bit. There's all sorts, you guys all know this. PPI, PE Alliance, GR33, all of those things are at your disposal. You can even use this if you'd like. You can make your own PowerPoint. And then, of course, feel free to call us. That's what we're here for, right? So if you guys have questions about it, that's what we're here for. And then, of course, knowing the standards. If you need to know a standard, that's not me. She knows. And then try to implement some of these best practices. Like I said, some of this stuff is common sense, but some of it, you know, folks might not know. So helping educate our customers, that's what we're here for, right? So.
And I'll add, you know, we talked about a new standard coming out that's being written, and if you don't know, the author of that is Mr. Harvey Skutlick, who's in the back of the room. So if you have, you know, questions about what that might look like and how things might change from what we talked about today, I would direct you to go find Harvey and see what he has to say about it. And I think sometime in the near future we'll all get to see that. So good work being done. What other kind of questions do you have, folks?
Part of my challenge is to take this great information and interpret it. I just want to repeat a couple things I heard. One is the reason we get weird looking beads, my word, not yours, is the heat soak beads cool a little bit during the heat soak, or the outer edges of them do. Is that correct?
Yes, sir.
And you mentioned that, Jesse, that the reason one side might be more double bead looking than the other is there might have been wind. I mean, wouldn't the best practice to use a tent even on a nice day? And that would mitigate some of that?
Indeed, you know, and sometimes with big, large pipe, that gets more and more difficult, you know, and a little bit of environmental factor on one side, difference from the other, can have a pretty significant impact during that heat soak on that bead. So I think you're more likely to see that cooling effect on one side versus the other when you're talking about such a large, you know, area that can be affected by wind. So.
Tarping the pipe too.
Yeah,
Tarping, all those kinds of things.
That one that you might have been referring to that has the double on one and the single on the other, we happen to know what that was from because we were on the job site. We were actually fusing on a pretty good incline. That was right. So he just asked, that didn't affect the quality of the weld, it just looked different, right? And yeah. Yes, sir.
Could you go back to the orange slide? I think it was like number 3 or 4 on the Alaska project with the 4-inch thick wall. The inside bead is going to be different also, and it's simply because you have 10 pounds of melt material on the face of this, and while it's squirting out and rolling back, the inside bead is also squirting down inwardly, and so it's going to have a higher, the bottom of that. Yeah. So it's going to squirt radially inward and can protrude a little bit more than you might think with a thicker wall pipe than a thinner wall pipe.
Yeah.
So, and I think that's a great point that Harvey brings up.
There,
24.
up one,
Nope,
25.
slide 24.
Yeah. So, that's a great point. I will also tell you that there is no standard in the world that addresses the inner bead. So, what happens though, is this project was a great example. The inspector walked down the inside of this pipe to go inspect the pipe. And he could see the inside bead and questioned it. So this was an education piece. This is back to know your customer and help educate your customer. That inside bead has no bearing on anything. There's no visual guide to it. There's no other things. And it can have some crazy different looking pieces, especially from the top of the pipe to the bottom of the pipe, exactly what Harvey said. But most people think about a 6-inch pipe. You're not gonna walk 50 feet down a 6-inch pipe on the inside and look at that bead. But a 2-meter diameter pipe, you walk up right down that pipe to that piece. But it's an education process. So help educate, help do it. If someone decides they want to remove that bead, you know what, that's okay. It doesn't affect it. The bead has no bearing on fusion joint strength itself. That's why people bead things in some cases. But it does become a question, and it does become something that you need to be able to answer and educate your customers about. So it is one that comes up, specifically came up on this project. I mean, Mike, you took a lot of calls on that project.
I think everybody did, yeah.
Sure.
Yeah, and percentage-wise, if you take a look at the height of that bead on the inside, if you compare the height of that bead, percentage-wise, 2-inch pipe versus 63-inch pipe, it's about the same
Yeah,
percentage.
it's about the same
So
protrusion.
it does not constrict the area, cross-sectional area. In fact, in big diameter, there's the water in the middle of the pipe doesn't even know the wall is there.
Well, this one was also weird because at 12 o'clock, it was one dimension, and at 6 o'clock, it was another 1.5 inches different. So the operators had to fuse 12 o'clock to 12 o'clock.
That was that alignment of the front light was
Yeah,
really
yeah.
good.
Yeah.
We spent quite a bit of time just rotating pipe.
So you were, you were also mentioning that from a best practice standpoint, go lower on your pressure on the scale and go, lower on your pressure. But also on that one example that you showed, they had a 25-second open-close time. Can you also say try to do it in 15 seconds, or is that just not safe and you don't have enough time to inspect it?
No, I think anytime you can reduce your open and close time, it's not a bad thing to do, and that, some of these pieces of equipment, it's harder to do that because you're moving a lot of mass of a heater, and there's certain travel with the carriage, requirements that have to happen to make that happen. But absolutely, to Harvey's point earlier about that big heater taking a long time to get out. We've got folks out there running our equipment that have extremely short heater removal times, and they're making adjustments to the equipment to make it happen. So, if that's available with the piece of equipment that you have, then it helps the process as they do it.
Isn't that part of the standard though? The amount of times to get the heater out is part of the ASTM standard, right?
Yeah, yeah.
That's one of our selling advantages that we have with McElroy. If you're in the US or Canada, you don't have these issues, but the second you step out and you go to Mexico or South America or somewhere else or Middle East with different equipment, their heater removal time is forever, right? And they're not meeting the standard. We can sell against that if your engineers and your inspectors understand the standard. they take forever to manually move a heater out and it's banging on stuff and the wind's hitting it and the sand and the dust, and that's a huge advantage for us on the McElroy side.
So, and it's twofold, and I think you hit that point, is one, it's about the cooling. You don't want any cooling to occur there. But it's also about the exposure. I mean, one of the things we're trying to do, minimize here, is any exposure to dirt or contamination on that joint. So the faster you can do that, the less it's exposed to air, wind, precipitation, anything, dust blowing in the wind, whatever it may be. So that combination of maintaining the heat for the fusion itself, but also eliminating and minimizing that exposure to any contamination is critical. So that is a huge advantage to the equipment.
Jim Brault down front.
Yeah.
What was that, what spec did you say that one illustration showing the double bead on both sides?
The perfect bead?
Yeah.
Or the one with the double rollback?
Double rollback.
PPI technical note 51.
51?
Yes, sir.
Okay. Technical note 51.
TN 51.
TN.
And I assume best practice would be if you find one of these, or you're on a job where one of these, I'll call it weird bead, after Peter here, especially like the double rollback on one side, not the other. It's smart to make a call to somebody early, and it's smart to have the data log joint so you can tell people what's really happening, not what you're assuming is happening, so that you can give us or anybody else the data to back up what's going on. So don't wait until you're 50 joints in and the inspector gets there and you say, I don't know, let me call someone.
Right.
Because now you've got a whole bunch of pipe fuse that you gotta hopefully convince them it's okay.
Yeah, there are also some validation checks along the way. When you observe that, let's say for the first time, there are some checks you can make, like, do I need to clock the pipe to make that difference in, to make the wall thickness match? Okay, you could have some strange difference based on that ID mismatch. Once you realize it, you can fix it, but you gotta kind of have everything else in control. Heater temperature, for example, left to right. The difference in bead appearance left to right may be okay. It may not be okay if you've got an issue with your heater. Once you can validate that you're where you need to be there, then the other things start to make a lot of sense.
Yeah, great points, and that's where documentation becomes so important, and not just what's in the joint report. You know, we're all guilty of it to a certain degree. When we start entering information into a data logger, it's real easy to hit that next button and go past the site conditions for the day. You know, that could be a critical step in identifying why something like that happened. So, yes, sir.
Yeah, I think the important takeaway here, or one of the important takeaways, is that these are not strange beads, they're different beads.
Yeah.
And they're different because they're bigger diameter, thicker wall. When you're fusing 12-inch DR11 and you melt back 1/4 of an inch, you're pushing back a 1/4 pound of material, and it's gonna form a rollback bead of a certain size. But if you're 4 inches thick and you're melting 1/4 inch, and you're pushing together the same amount, you're pushing out, I'm gonna say, 1.5 pounds of material, and it's gotta go somewhere.
Right.
And it's gonna go into a bigger, fatter, different shaped bead because you're moving more mass. So I think the part that we should take away is we need to educate ourselves that large diameter fusion beads are not gonna look the same as DR11. And now we need to look at them as we're seeing up here and say, this is the normal thing for big diameter, thick wall pipe.
Mike,
This is really good data, by the way. I think it's educational, and I think from a best practice standpoint, I'll tell you what my perception is, and maybe you guys are all doing this in the room, but anytime I deal with a thick wall, heavy wall job, a lot of times it's on a directional drill job, or it could just be just big heavy wall pipe. I think it's always smart to get all of that out of the way before you start your pipeline project. Get everybody together, including the inspector. Let's go through the fusion process. Let's destructively test a joint. Let's look at the data logger. Let's do all of those things, but let's do all of that ahead of time so now everybody's on board. So down the road, when you get a funky bead, they go, well, did we do a destructive test? Let's do one now. Let's check it. Let's check the data logger. Let's make sure Matt did the same fusion he did 50 joints ago. You just eliminate a lot of that noise, because we all know inspectors can make your life miserable if you don't understand what's going on. Do it early on the job, and then even to add to that, you can test the pipe at the factory before it gets to the job site. Let's do a high-speed tensile impact test. Is the pipe good? Yep. Gets to the job site. Is the operator good? Let's qualify him, but let's do it while the inspector is there. Bring him in, and what we've done in a lot of cases is, let's hold a big fusion class, demo day, but everybody's gotta be there, including the inspectors.
And your engineers, the engineers
And
are a big
engineer.
part of this as well. So
Correct.
if it's a spec person who's going to make a decision, then you get everybody and educate everybody who's potentially going to
Absolutely.
make a decision.
And tying it into the data logger is really important, but doing those guided side bend tests are extremely important. Whether it's 1 in 50 or 1 in 100 or 1 every week or whatever it is, that I can sleep at night knowing those joints are good.
And read TN 51 and hand it out to your friends, families, contractors, and distributors.
There you go.
Yeah, plastic pipe institute.
Grandchildren.
Yeah, but we're, with the guided side bend test up in the Marcellus, we're telling our customers and contractors to use the side guide bend test for large diameter, but they're still using, I know Jim, we've talked, they're still using the McElroy infield tensile testers. Testing at 12, 3, 6, and 9 on the pipe. One could be a perfect joint, all 4 pass. Another one, perfect analog joint, 1 will fail. Then they're looking at pipe, they're calling us. Now they're inspecting pipe. Now they're looking at, now there's windows when they look up the light, and it's just getting kind of ridiculous just because it's the infield tensile testers. They'll just give a false fail out of nowhere, because they shouldn't be used for larger diameter, to pick the wall. So that's a big issue we're running into up in Marcellus.
Interesting. Following what Mike James said and Chris, I will recommend to go for ASME Section 9 that give a guidelines for qualification and validation before you start your pipeline project, and give you the step-by-step, using data logger, qualifying in the infield test and the guide side bending test for over 1 inch. So I would say everything that's being said here, before we start a project, ASME Section 9 give you a great tool, to validate. And also, something that we haven't touched here is large pipe, diameter. Also means differences in between the temperature from the top and on the bottom when you are outside, and also related to the heater.
Sure.
So if you add those variables, then you have problems. So that's why you need to capture the 5 variables that ASME Section 9 asks you for. Qualification of the operator, the machine, infusion machines, pipe, and temperature condition and weather condition. So this is something that is highly recommended.
Yeah, absolutely. Got any other questions?
I'll just say, this has been a great conversation. It's just really cool to have so many people from different organizations
Yeah.
that might be competitors tomorrow sitting here all learning from each other. So I
Yeah.
really appreciate the back and forth. We're all learning some good stuff, so thank you.
Harvey, were you about to drop some more knowledge on us?
No, I was just gonna, you brought up a good point. If you're dealing with a 12-inch heater plate, it's just this big, and the temperature is very uniform. When you're dealing with a big diameter heater plate, it has to be a little bit thicker, but also it's so big in diameter that when it's sitting there in position, the heat is rising.
Sure.
And so it's rising up, let's say it's 8-foot diameter pipe, it's rising up 8 feet, so you get a convection current.
Mhm.
And at the top, it may be 560, but at the bottom, it could be 400.
Yeah, absolutely.
Because the wind, the convection, is cooling. So I think in our standard, and you just made me think of that, is to check the temperature all around, but especially the temperature at the bottom.
Yeah.
Because your weakest link is
Yeah.
cause problems.
Yeah, absolutely. Awesome.
Everybody give a big round for that.
Keep it going. I want the guys next door to be jealous. Thank you, guys.